So today we are going to discuss few more problems from the rotational motion, and one of the problems, or we can say the problems which we are going to discuss today, is based on our one of the, in general it is sometimes called as a yo-yo problem also. Okay. And so let's start with our common rotational motion problem, and it states that a small bead of mass m is free to slide without friction along a smooth straight road that lies in a horizontal plane and rotates with a constant angular velocity omega about one of its ends. The effects of gravity are neglected. So based on this, we are having three questions. Part A: show that r is equal to r naught e raised to power omega t is a possible form of motion for the bead, where r naught denotes the initial distance of the bead from the axis of the rotation. And in part B, for the motion described in part A, determine the magnitude and the direction of the force exerted on the bead by the rod. And in part C, for the same motion, compute the power delivered by the external agency that maintains the constant angular speed omega, and show by direct calculation that this power equals to the instantaneous rate of change of the bead's kinetic energy. So this is multiple concept question. So first of all, let's draw the basic figure. So we are given that we have a straight rod and it is fixed at, suppose, this end, because it is going to rotate along this direction with the angular speed of omega, and at somewhere to the other end we have a bead. Okay. And the distance of the bead is, suppose, given as r. Okay. And the mass etc. are given to us. Okay. So in this case, in the first part, we have to find out that we have to prove this particular relationship, r is equal to r naught e raised to power omega t. So for that, we can assume that, let us suppose this is our x-axis and our y-axis, and this rod makes an angle of theta with respect to positive x-axis. So therefore we can write the polar coordinate of the bead. So we can say that, and this is our bead, and we can write that, and we assume this point as origin. So we can say the polar coordinates will be equal to and this will be equal to our r comma theta, and therefore we can write for any instant t, for any instant t, we can write the equation that our theta of t will be equal to our angular velocity multiplied by time t. Okay, that is a basic relationship. And for the sake of simplicity, let us avoid this t written with theta. So this can be written as theta is equal to omega t. Now if we differentiate this equation one time, we are going to get this as theta first derivative will be equal to omega. Okay. And its second derivative will be equal to 0. So it basically means that the bead is constrained to move only in one direction, that is along the rod. Okay. So from here, because we got this value is equal to our 0 and our, you can say, single derivative theta is equal to omega. So therefore from here we can say that the bead is constrained to move only along the rod. So therefore we can say that its only possible motion is radial. The only possible motion is radial, and that is our r of t. So let us come to our first part, that is our part A, in which we are supposed to find out so we start with our part A, in which we are supposed to prove the relationship. Okay. So therefore we have just written that our bead is at a distance r from the origin. Therefore we can write that the position vector of the particle can be written as our r vector will be equal to our r, and we can take a unit vector E of r, which is along the radial direction. Okay. So in this, our r is the distance, or we can say magnitude basically, and this unit vector is our unit vector in radial direction. Unit vector in radial direction. And so if we differentiate this equation once, we are going to get the velocity. Okay. Therefore we can write that velocity in polar coordinates and we differentiate with respect to time t, and we are going to get this as our r vector single dot, and this will be r vector r magnitude single dot, and this is our a unit vector plus r, and this will be our unit vector, its derivative with So this will be our its first derivative, which is our velocity. Okay. So in this case we can say that the unit vector, which is our E of r as well as E of theta, are not constant. Okay, because our rod is rotating and we have taken this as our theta, and the rod is rotating in this direction. So therefore the direction as well as the unit vector is going to continuously change. So our theta is also going to change and our unit vector is also going to change, which is representing the radial direction. Therefore we can say that our unit vector ER unit vector and E theta unit vector are not constant. They rotate as theta changes. So it means we can write that their time derivative it will be giving us time derivative of our E of r will be equal to theta derivative and our unit vector theta, and similarly our theta derivative will be giving us minus, and this will be theta derivative, and this is going to give us a unit vector. And so our expression for this velocity, if we substitute these two time derivatives, we can write that our velocity v, which is equal to over r single derivative, will be equal to r derivative and unit vector, and here we get r theta derivative, and this will be over E theta unit vector. So it means this is the position, this is the polar coordinate velocity in terms of polar coordinate, and here it is having two components. One is our radial component and other one is our transverse, or we can say the tangential component. So from here we can say that the radial component is our r unit derivative, and we are having our transverse or we can also say tangential, that is our r times unit vector first derivative of our theta. And therefore we can write from here, we can easily find out our acceleration also. So we can say our acceleration, that is our a, will be equal to derivative of our velocity, and that will be giving us our r double derivative unit vector plus r single derivative unit vector first derivative plus r single derivative theta single derivative, and this is our e of theta plus r theta double derivative and e unit vector of theta, and this will be finally our r theta and e single unit and its derivative. Now we can easily substitute these two equations. This is the first one and this is our second one. Therefore, from here we get that our acceleration will be equal to r double derivative unit vector plus r single derivative theta single derivative, and this is unit vector with respect to theta plus, and this is r single derivative theta single derivative unit vector of our theta plus r theta double derivative and our unit vector of theta, and this will be plus, this will be r theta single derivative, and this is multiplied by minus theta single derivative, and this is our e unit vector. And once again we can find out the radial component as well as the transverse component, and so we get the radial component. Radial component will be giving us E of r is equal to r unit vector double derivative minus r theta square and a single derivative. Okay, and then is our transverse component, which is our E of theta will be equal to r theta double derivative plus, and that will be equal to twice r single derivative theta single derivative, twice r single derivative and theta single derivative. Okay. And we can also write our acceleration in terms of, if we manipulate the equation, we can write this as our r double derivative minus, this will be r theta square multiplied by unit vector with respect to r, and this next comes our transverse component, that is r theta double derivative plus twice r single and theta single multiplied by e raised to power unit vector theta. Okay. And in the given question we have said that it is rotating with the constant velocity, constant angular velocity, that is omega. Okay, that is given in the question. Therefore we can say our single derivative is the representation of our omega and its double derivative is our 0. So if we substitute, we get our A of r. So radial component will be equal to r double derivative, and this comes as r omega square minus r omega square, and A of theta, we get this as our double derivative is equal to 0, so this comes as twice r twice omega r single derivative, twice omega r single derivative. So this entire calculation was only to find out the radial component as well as the transverse component. Okay. Now we come to our main part of the question. If you know these two formulas, you can just put it and solve it and get the answer. Okay. And so if you know the formula, you can just directly start by writing these two equations. Okay. If you don't know, you can just try to solve this. And it is given in the question actually that the rod is smooth, or we can say there is no friction. It means if there is no friction, then the rod can only exert a normal force. Okay. Therefore, we can say that rod can only exert a force normal to itself. Normal to itself. Okay. And or we can say it cannot exert a force along the rod, which is radial direction. So from here we can also say that it cannot exert a force in radial direction, that is along the road, along the rod. Okay. So there will be no radial force, and therefore we can write that our m times ar, so we can say our radial force let us suppose that is our Fr will be equal to 0, or we can write this as our mass into radial acceleration will be equal to 0, or in terms of our derivatives we can write this as our, because mass cannot be equal to 0, therefore ar is equal to 0, or we can say this r double dot is equal to 0. So from here we can say that our ar will be equal to 0, and therefore we can write that our r double dot minus omega square r is equal to 0. Okay. Now this is our, you can say, a linear equation, or we can say ordinary differential equation. Sometimes we also call this as ODE. So this is our linear ordinary differential equation, and its solution is, general solution will be given as r of t is equal to a e raised to power omega t plus b e raised to power minus omega t. And in this case we can say that considering a special solution, such that our b is equal to 0, therefore we can write that our r of t is equal to our r naught e raised to power omega t. And so this is our part A. And now we come to our part B. and part B it says that determine the magnitude or direction of the force exerted on the bead by the rod. Okay, so we have to find out the direction and the magnitude of the force exerted by the bead. And we just found out that the only force that is being exerted is the transverse force, because the radial force is equal to 0. We just proved it here. F of r is equal to 0. So we can say the rod exerts only transverse force. Let us suppose that is our f of theta. So therefore we can write that our f of theta will be equal to m times a of theta, and we substitute a of theta, we get this as m times 2 omega and r first derivative. And we know, we just derived a relationship that our r is equal to our r naught e raised power omega t. Therefore its first derivative will be equal to omega r naught e raised power omega t, and this term is nothing but our r. So we get the first derivative is once again equal to omega times r. Therefore we can write that our f theta is equal to, this will be equal to our twice m, and it will be omega square r. Okay. And so this is our magnitude, and the direction is in positive theta direction because it is rotating in the positive direction. So we can say it is positive theta direction. Okay. And or we can say that is tangential and because our first derivative, that is our r first derivative greater than 0, so this gives us that a of theta will be also greater than 0. So direction will be over in the positive sense. Okay. And the radial force is equal to 0, so there will be as the radial component is 0, so radial force is 0, which I have already discussed in the initial solution. Radius force is equal to 0. So we come to part C, and in the part C we are supposed to find out the power supplied by the external agency. And so in this case the power will be used to move the rod in with a constant angular velocity, or we can say the power, external power delivered by the agency will be used to maintain a constant angular speed. Constant angular speed, or we can say it should be sufficient to provide a torque so that it moves with the angular velocity omega. You can say the power given by agency maintains maintains rod's constant angular velocity, maintains rod's constant angular speed, and which will be equal to, or we can say equals, the torque it supplies times omega. So we can say our power P is equal to f of theta multiplied by velocity in terms of theta, and this we can write f of theta, and velocity can be written as r multiplied by our omega, and f theta we already know, so we substitute it here and we get this as 2m omega square r multiplied by r omega. So this gives us that the power P will be equal to 2m omega cube, and we have our r square. Now we are going to find out the bead's kinetic energy. Bead's kinetic energy, and let us suppose that is given as k, and we know that is our half m v square, and velocity we already know the equation is our r single dot square, and r single dot and plus r theta whole square, and we can just solve it. We get our kinetic energy is equal to our half m, and we get this as r square plus, and we know that our theta is our derivative of theta is nothing but omega, so this comes as our r square and omega square, and we know that our r single dot is equal to omega r, therefore its square we can write this as kinetic energy is equal to over half m, this will be equal to over omega square r square plus omega square r square, and this will be giving us half m, it will be 2 omega square r square. So here 2 and 2 cancels out, so we get the kinetic energy is equal to m omega square r square, and we are going to differentiate with respect to time, so we get this dk upon dt will be equal to, we have our m omega square, and this comes as our twice of r, and we have this as our r single dot, and we already know, so let me write it here. So we get our derivative of our time, derivative of kinetic energy with respect to time will be giving us twice m omega square and we are left with r and r dot. Okay, so we get this r, and our r dot is nothing but our omega times r, so this gives us twice m, and we have a omega cube, and this comes as a r square. Therefore, this relationship, that is a derivative of our kinetic energy, is same that is our of power delivered, so which were asked for. Okay. So this is equal to our power of the power delivered by the external agency, which was asked for. So we come to next question. It states that a solid cylinder of radius r and mass m rolls down an inclined plane that makes an angle theta with the horizontal. The coefficient of the static friction between the cylinder and the surface is mu. Determine the maximum angle theta for which the cylinder rolls without slipping on the inclined plane. This is a basic about the rolling cylinder, which is rolling without slipping down the inclined plane. Okay. So let us draw the basic figure for that. So we have inclined plane and we have angle of theta, and we have a cylinder, and its radius is suppose given as r, and it is rolling in the downward direction. So we are going to have an angular acceleration of alpha, and the friction is going to provide the torque that is going to act in the upward direction, and we can say that it is having a linear acceleration of our a in the downward direction. And the forces that will be acting, we are going to have our mg, and there will be a normal. Okay, so these are the basic down the inclined plane. Okay. And our mg can be divided into two components. So this angle will be over theta, so we are going to get this as mg cos of theta, and here we are going to get our mg sin of theta. So based on this, we can simply write our equation, and we can say that our normal n will be equal to mg cos of theta, okay. And we can also write the translational equation, and it is moving downward with the acceleration of a. Therefore, we can say that our mg sin of theta minus frictional force is equal to mass into acceleration. Okay. And we can also write its rotational equation. So we have our rotational equation, and for rotational equation, because there is no slipping, only rolling is there, so we know that our a will be equal to alpha times r, and the torque is equal to I times alpha, and the torque will be provided by our frictional force. So we can say our torque is equal to frictional force F, and perpendicular distance is r. So we simply substitute that, we get this as F times r is equal to I, and I is a moment of inertia, which is our half m r square, and alpha we can write as a upon r, and here this square goes by r, and this r goes by r, and we get from here that our frictional force will be equal to half m times A, and we substitute it into the translational equation. So let us suppose we call this equation number 1. So we can say from equation 1 we get this as mg sine theta minus half ma is equal to m times A, and we move it to the right side. That will be giving us 1 plus 1 by 2, which is 3 by 2, and we can simply remove our m, and from here we get that our g sine of theta is equal to 3 by 2 A, and we can see that our A will be equal to 2 by 3 g sine of theta. And now we can find out the magnitude of our static friction. So we can say our magnitude of static friction, and that is equal to our F should be equal to our half m times A. This is already we only found out. So here we substitute value of A, and we get our F is equal to half m times 2 by 3 g sine of theta. 2 and 2 cancels out, so we get this friction is equal to 1 by 3 mg sine of theta. Okay. And we know that for rolling without slipping, the required static friction must not exceed the maximum static friction. That is a basic condition. Okay. So we know that for rolling without slipping, required static friction must not exceed the maximum static friction. The maximum static friction. And we just found out the required static friction, which is our F. It should be less than equal to our F max, and F we got as 1 by 3 mg sine of theta should be less than equal to our mu times n, which is mu, and normal is our mg cos of theta. And here g cancels out, so sorry, here it is 3, and therefore we get our tangent of theta should be less than equal to 3 times mu. So this was our solution which it asked for value of theta. Next question. Okay. So in this question it states that a solid disk of mass m and radius r is wound with a light inextensible tape. The tape passes over a smooth frictionless pulley and a mass m is suspended from its free end. The disc is allowed to drop vertically as the tape unwinds from it. So based on this, we have two questions. Express the linear acceleration of the suspended mass A and the disc capital A in terms of angular acceleration alpha of the disc. And part B determines the value of A, small a, capital A, as well as our alpha. Okay. Sometimes these type of questions are also called as a yo-yo. Okay. And means, first of all, let me draw the basic diagram. So we are given that okay, so we have a fixed pulley and over this fixed pulley we have a tape that is wound on it, passed through it, not wound on it, but it passed through it, something like this. And to the other end there is another solid disc. Okay. So to the other end there is a solid disc, okay, and around it the tape is wound, something like this. And to the free end we have a mass m, and this is fixed. Okay, so we have two pulleys, and in this case we have to keep in mind that this mass, as it is going to fall in the downward direction, its acceleration is given as a. This tape is going to unwind itself, so which basically means that, let me call this as our disc 1 and this is our disc 2. So this 2 is having a tape around it. Okay, it will be something like this. This is disc 2 and we have tape and this is wound about it. And if the disc 2, as it is going to fall in the downward direction, the tape is going to extend. Okay, so there will be two types of motion that will be associated with the disc 2. One will be, it's a rotational motion, and other one will be in the downward direction with the acceleration of a. Okay, so there are two types of motion that is associated with our this disc D2. So it is given that it is moving with angular acceleration, so it is going to have an angular acceleration of alpha, and a linear acceleration in the downward direction is our a. So first of all we have to find out the relationship that is between our small a, capital A, and angular acceleration alpha. Okay. And some in terms of this pulley system, it is also called as a constraint relationship. Okay. And we can clearly see that our acceleration A, as it is moving in the downward direction, the disc D2 is going to unwind itself and further move in the downward direction. So it means we can write that the acceleration of the hanging mass which we have taken as a will be equal to acceleration of the point on the rim of the tape unwinds. Acceleration of the point on the rim where the tape unwinds. So suppose we can take any point, so let us take this point, and as it is going to move in the downward direction, this point is going to have a linear acceleration of our a and angular acceleration of our alpha. Therefore, we can write that our a will be equal to linear acceleration of our that particular point and r times our alpha. This is the constraint relationship between our these two. All these are accelerations, the linear acceleration as well as the angular acceleration. Okay. So this is the important part in this. Now let us consider, now it is quite simple. We are going to consider the tensions and everything, and that is going to solve our purpose. So we have a mass m, so there will be a tension T in the upward direction, okay, and we are going to have a mg in the downward direction, and there is our disk whose mass is given as capital M. It is going to have our mg in the downward direction, and there will be tension T, but that will be at one of the ends, and it is also going to rotate. So this is a basic figure for that, and so we can write the equation for, first of all, let's write for the hanging mass m. So we can say for hanging mass small m, it is moving in downward direction with the acceleration a, and here it is acceleration capital A. Alpha is the angular acceleration. So we can say that our mg minus t is equal to mass into acceleration. Okay. Now the disk is having two types of motion. One is our translational, other one is our rotational. It is moving downward as well as it is rotating. Okay. So we can say for the disk, we are having two motions. One is our translational, and translational, it is moving in the downward direction with acceleration a. So we can write this as our mg minus t is equal to mass into the acceleration, and then it is going to have a rotational motion, and for that there will be torque acting. So we are going to consider the rotational. So there will be torque that will be being generated by tension T, and it is at a distance r from the center, and the downward direction we have our mg. Therefore we can say that for rotational we can write our torque tau is equal to moment of inertia multiplied by the angular acceleration, and this torque tau is equal to our tension multiplied by perpendicular distance T multiplied by r. So we get this as our TR is equal to, we can substitute value of our moment of inertia, and that will be equal to our, it is a solid disk, half m r square times alpha, and here r goes with r, therefore we get our tension T. So we get our tension T is equal to half m r times alpha. And in part A, we already calculated the constant relationship, that is small a is equal to, so we can say that our a is equal to a plus r times alpha. So from here we can say our alpha is equal to a minus capital A divided by r, and we are interested in finding out. Okay, so we are going to use this relationship mg minus t is equal to ma, and here we are going to put t. Okay, so let me write it here. So we have mg minus t is equal to m times a. Substituting our tension T, we get this is mg minus half mr alpha is equal to m times our a. One second. One second. Oh, sorry. We have to use this equation. My mistake. So let us call this equation number 1, and this is equation number 2. So from equation 1, we have our mg minus t is equal to m times a, and we substitute our t, we get this as mg minus half mr, and in place of alpha we can put a minus capital A divided by r. So this comes as a minus capital A divided by r is equal to mass into acceleration. And this we can cancel out our r and r, therefore we get our mg 1 by 2m a minus capital A is equal to m a small a. And similarly we can use equation number 2. So we can say from equation 2 we are going to get our mg minus 1 by 2 m a minus a is equal to m times capital A. And we can simply simplify it, and let us call this equation number 3 and equation number 4. So from equation 3 and 4, from equation 3 and 4, we can say that our Okay, if you solve these two, we are going to get that our acceleration A will be equal to mg plus 1 by 2 times ma and divided by m plus 1 by 2 times capital M. And let me write it directly, otherwise. Okay, that's a simple calculation. I think we can sort it out easily. So we can say acceleration A, capital A, will be equal to over m plus capital M times g, and this comes as 2m plus 3 times m. And I think this will be sufficient. I think this is the thing only asked. Determine the value of A. Yes, so these are the only two things that are asked for. It will be only calculatory part to solve these two things and get the value of A as well as our capital A. And if you need to solve further, we can substitute value of A and get the value of small a in terms of capital A also. Okay, so that is only part of our calculation. There is not much of things that are required now. So in this case, we have to remember specifically that the disc on which the tape is wound is going to rotate as well as it is going to fall down. Okay, so that's why sometimes it is also called as a yo-yo problem. We are also going to do another problem, which is similarly we can call this a yo-yo, and there is it states that a drum A of mass M and radius R is suspended from another drum B also of mass M and radius R. Drum B is free to rotate about its fixed horizontal axis. A massless inextensible metal tape connects the two drums by being wound around their outer surfaces, allowing it to unwind freely as shown. Okay, I'll draw the figure. And gravity acts vertically downward and both drums are initially at rest. Determine initial downward acceleration of drum A, assuming it moves straight down without any lateral motion. So in this case, we have two drums A and B, and they are connected by a metal tape. So we can just draw an approximate figure for that. So we have a drum B which is fixed, and around this drum B there is a tape which is wound, and it is connected to another drum B, A. So we have, this is drum B and this is drum A, and so in this case what is going to happen, that as drum B is going to rotate, so because of this the drum A is also going to rotate as well as it is going to fall in the downward direction. Okay. And the tape will be, you can say, collecting on it. I think it is mentioned there, one second. The two drums by being wound around their outer surface allowing it to unwind freely. Okay, so it is only unwinding freely. Okay. So one second. So we have a drum radius suspended from the drum. Also this drum B is freely rotated about the horizontal axis. Connects the two drum by being wound around their outer surfaces. Okay. So they will be rotating as B will be fixed and A will be moving in the downward direction. And because B is fixed, so only A is moving. So let us suppose it is moving downward with the acceleration of A. And now we can draw their diagram separately also. So we have our B and mass is given as capital M. Its radius is our capital R, and there will be tension T for our B. And similarly we can draw for our A, and it is having a mass M. This is radius is same, that is radius of R, and it is connected with the same tape, so tension will be T, and it will be rotating. And let us suppose it is rotating with the angular acceleration of alpha. Later on we can just modify if required. And in the downward direction there will be a force that will be over mg, and it will be moving also in the downward direction with the acceleration of our A. So this is our basic figure. So first of all, we are going to find out once again the constraint relationship between the two. Okay. And in this case, we are going to find a constraint relationship using a little bit traditional way, because in normal we assume that if there is a movement of one of the block by a distance x, and then we can you can say use that x to the other part also. So therefore we can say we are going to find out the, so let us suppose that drum A descends by small distance, that is our delta x. So it means that length of the tape between the drums increased by delta x. Length of tape between drums increase by delta x. And both drums are rotating, therefore we can say our delta x will be equal to, because the radius is same, so this will be r, and this is the angle of rotation of A plus r angle of rotation of our B. Okay. These are the small angle, that is because both A and B are rotating. And if we differentiate, double differentiate them, because this is nothing but our distance, and this is going to give us our, this is distance but in terms of our polar coordinates. So if we double differentiate it, on the left side we are going to get acceleration, that is our A, and on the right side we are going to get our angular acceleration of A as well as angular acceleration of our B. So this is the constraint relationship between the two. Now we come to our torque as well as the forces. So like we said, there is a tension T, and our A is moving downward as well as it is rotating. So A will be having two types of motion, translational as well as rotational. So we can say our for drum A, air from drum A. Let us consider first of all translational. And translational, it is moving in the downward direction. So we are going to have our mg minus t is equal to mass into acceleration. And then we are having rotational. And rotational is our torque tau, which is equal to moment of inertia multiplied by angular acceleration. And our torque will be also equal to tension multiplied by our radius. And the moment of inertia of our I, which is our standard formula, that is half mr square. And okay, so rotational, let me solve it for A first of all, because rotational will be for both A as well as B. Okay. So this basic equation is going to hold true for both. This will be true for A as well as B. This will be also true for A as well as B. And this is true for our A as well as B. Therefore, we can write that our alpha of A is equal to over alpha of B, and that will be equal to over tension multiplied by radius, moment of inertia, which gives us T upon R, and this is our half m r square, which gives us square goes by this r, and it comes as our 2t divided by m times r. So let us assume that they are having same acceleration, alpha A is equal to alpha B is equal to alpha, and that is equal to 2t divided by mr. Okay, so this is the angular acceleration. Now we are going to use the formula constraint relationship which we just found out. So we know that our A is equal to R, and we have our alpha of A plus alpha of B, and alpha of A, alpha of B are equal to alpha, so this comes as 2R times alpha. And alpha we already know, so this comes as about 2R times 2T mr, and here R and R cancels out, so we get that our A is equal to 4T upon m. And we already know the relationship that our mg is mg minus t is equal to ma. Let us call this equation number 1. So from equation 1, we get this as our mg minus, sorry, here I have to find out the t. I found out a, so this is that t is equal to ma divided by 4, and we are going to substitute t. So this comes as our ma upon 4 is equal to m times a. And now this mass cancels out throughout, therefore we get this is equal to our g minus a by 4 is equal to a. So this gives us 1 by 4 plus 1, that is 5 by 4. Therefore we get our A is equal to 4 by 5 times g. So this is the acceleration of our drum A. You can say initial acceleration of drum A is given as small a, which is 4 by 5 times g. And if we require to find out tension, we can also find out our tension T, which will be straightforward. Tension T is equal to, we know it is MA multiplied by 4. So we substitute our A, and this comes as our M upon 4, and A is our 4 by 5 times G. And here 4 and 4 cancels out. So this comes as our mg upon 5. And if required, we can further solve it for alpha also. So alpha is equal to A upon 2r, and this comes as our 1 upon 2 times A is 4 by 5 times G, and 4 goes by 2, so we get this A will be equal to 2 by 5, and we have G upon R. Okay. So these are the few of the things which we solved for. Okay. So these were the questions for our this particular video, especially about the yo-yo motion. And in the yo-yo we have to remember that which is rotating, which is falling down, is also going to rotate. Okay, so based on this we did 2 yo-yo types of questions. Okay. So this completes today's. Thank you.